chemists don't usually use proportions and percentages that much. Those ideas are true, the proportions are the same, but we tend to look more at the particles and look at the ratio of atoms of each element. And that is the fundamental underpinning for those constant compositions. The constant composition with respect to mass is because they're composed of atoms in fixed ratios. The 18 grams of oxygen to 2 grams of hydrogen is because there's 1 atom of oxygen to 2 atoms of hydrogen. They don't weigh the same, and so the ratio of atoms is different than the ratios of masses, but they're always going to be constant. So in chemical formulas, what we do is we represent the number of atoms of each element present in the compound. And we do this using subscripts. We have a lot of subscripts and superscripts in chemistry. We use subscripts to indicate the number of atoms of each element, and by convention, we don't use the subscript 1. So there's the chemist's bias against the number 1 again. I'm surprised he hasn't sued us. So common formulas, NaCl is the chemical formula for table salt. Na is the symbol for sodium, Cl is the symbol for chlorine. And this indicates a 1-to-1 ratio. We don't write the number 1 as a subscript because we don't need to. If it was 0, we wouldn't write Na at all. If it was 2 or 3 or some other number, we're going to write that number. So just the fact that we wrote Na means there's 1. CO2 is 1 carbon, 2 oxygens. So you put the element symbol, and then after it comes the subscript telling us how many. So 1 carbon and 2 oxygens. This is 1 sodium and 1 chlorine. Here's table sugar, C12H22O11. A lot more atoms in this guy. 12 carbons, 22 hydrogens, and 11 oxygens in a ratio, 12 to 22 to 11. And these are always going to be whole numbers. You can't have part of an atom, just like you can't have part of a person, right? Two compounds that are somewhat similar and yet very different. Both made out of carbon and oxygen, CO or CO2. These subscripts are important. You change the subscript, you change the compound. You change the compound, you change its properties. Carbon monoxide is very dangerous. It's produced when you have combustion without enough oxygen present, like you've got a gas heater and it's not properly vented, it's not getting enough oxygen. It can fill up your house with carbon monoxide, which can kill you. Because when you breathe in carbon monoxide, the red blood cells, the hemoglobin in your body, has a preference for carbon monoxide over oxygen. And so it will bind to the hemoglobin in your blood and you will suffocate even if there's plenty of oxygen present. It's very bad stuff. Carbon dioxide, on the other hand, is pretty much harmless. You breathe oxygen in, you breathe carbon dioxide out. There's a lot more carbon dioxide in the air than there is oxygen. But that's fine. That's how everything is supposed to be. Now, could you suffocate if you had too much carbon dioxide? Sure, but it's not the carbon dioxide that's hurting you. It's the lack of oxygen that would be hurting you. So, relatively harmless, 1 extra oxygen. Harmful, with 1 less oxygen. So we have to be really precise when we write formulas. We also need to be careful with our capitalization. You know, when things are typed out, that's fine. But sometimes, well, that's just even a really bad excuse for a lowercase o. CO, this is different than CO. This is capital C, capital O, carbon monoxide. This is capital C, lowercase o. This is cobalt. That's a metal. Very different. So we have to be very careful that we make our capitals big and our lowercase letters small. In general, chemical formulas are going to list the most metallic elements first. So if there's a metal, that one will come first. If you've got two nonmetals, then the one that's closer to the metals in the periodic table will generally be first. So if we look at sodium chloride, we always put sodium first and then chlorine. We don't ever write the chlorine first and then the sodium. Why? Because we decided to do it that way. When you address a wedding invitation, Mr. and Mrs. John Smith, and you send it off and you hope they'll come to your wedding. Why do we write Mr. and Mrs. and not Mrs. and Mr.? Because that's how we've always done it, right? It's just how we do it. It doesn't really have anything to do with feminism or anything like that. It's just that's how we do it. And so this is how we do chemical formulas for compounds. Metal first, nonmetal second. So I find in many ways that the metals remind me of men. I think of the metals as being masculine, and the nonmetals then are non-masculine. They end up being feminine. So this is just like the wedding invitation. Mr. and Mrs. Metal first, then the nonmetal. Well, what if you have two that are nonmetals? How do you choose? Well, you look at the periodic table. Between nitrogen and oxygen, which one is closer to the metals? Nitrogen. So we're going to put nitrogen first. We do have a particular order that we put these things in. Now, would I understand what you meant if you wrote ON2? Yeah. But it's like, a 3-year-old talking to you and they're mixing up their words. And it's really cute and everything, but at some point we need to learn how to say it the right way. So the metal first is just kind of the general thing. If you want a real specific list, there's the specific list. I am definitely not going to make a really big deal out of this. Yeah. So write a chemical formula for each compound. The compound containing 2 silver atoms to every sulfur atom. We need the symbols for these elements. What's the symbol for silver? Too many S's. Ag. So Ag is a metal, right? And what's the symbol for sulfur? S. And sulfur is a nonmetal, and so silver goes first, and the nonmetal goes second. And then there's 2 silver atoms, so I'm going to put a subscript 2 after the silver symbol, and after sulfur I'm not going to put anything, because I don't need to write the number 1. How about B, the compound containing 2 nitrogen atoms to every oxygen atom? What's the formula? N2O. That's kind of dumb because that was the example on the previous page. So I should fix that, but it's not going to happen. Compound containing 2 iron atoms to every 3 oxygen atoms. Fe2O3. Iron is one of those funny ones. You might think it's IR, but IR is iridium. Fe comes from ferrum. So Fe2O3. Any questions? Some chemical formulas have groups of atoms that act as a unit. These are a little bit like buying a game system at Costco. You don't just get the game system, right? It's going to be packaged together with, an extra controller and 3 games or something. It's this package deal. It's a bundle, right? A bundle pack. It's all shrink wrapped together, and you can't just get part of it. Polyatomic ions. Poly meaning many, atomic meaning atom. These are ions that have many atoms in them, and they're a little bit like that bundle pack. They come as a unit, and they stay as a unit. And so when we have two or more of those, we're going to set their formulas off in parentheses. The parentheses are kind of like the shrink wrap. And then outside, we're going to put a subscript that tells us how many of those packages we have. I think I've got examples. Yeah. So here, Mg, and then in parentheses is NO3, and then outside is the 2. So NO3 is the symbol for the nitrate group. This is a polyatomic ion that has a special name. And the reason behind it is no more significant than why did we name him Tommy. Well, we named him Thomas, actually, but let's go with Michael because he doesn't really have a nickname. Why is he Michael? Because that's what we named him. And so I believe that nitrate is one of the ions that I put on that list of memorization things, because it would be really helpful if you just memorize that nitrate is NO3 minus. There's not really any logic or reasoning or explanation behind it. It's just its name. But nitrate is a polyatomic ion. It acts like a unit. And so when we have more than one of them, we put shrink wrap, parentheses around it, and we say how many of them on the outside. Because what we don't want to have happen, let's look what would happen if we left the parentheses out. Doesn't that kind of look like 1 nitrogen and 32 oxygens, right? And we also don't want to do something like this, where we have to go and multiply all the way through, because then it's very hard to recognize that that has the NO3 group in it. It's not that we took 2 of those bundle packs from Costco and combined all the pieces into one giant thing. No, we have 2 packages. And so the shrink wrap, the parentheses, tell us this is a polyatomic ion on the inside, and on the outside this is how many. If there is only one of them, we don't need the parentheses. So if we had, let's fix this up a little bit, something else. If we only had one of them, then we don't need the parentheses, because we're not going to write things that we don't really need. What about the negative? Well, we'll learn about stuff like that in a little bit. Magnesium forms an ion, doesn't it? What charge does magnesium ion have in the periodic table? +2. And each of these has a -1 charge, and there's 2 of them. And so the 2+ from the magnesium and 1- from each of the 2 nitrates combines, and overall it all adds up to 0. And we'll get to that, I think, later in this chapter. Yeah, this is chapter 5. What we need to understand at this point, though, is if we're counting up how many atoms of each element there are, this is just like in math when you had, 2 times 4 + 7. It distributes. So the 2 on the outside of the parenthesis applies to everything inside. If you have a game system with 3 games and you have 2 of those bundle packs, how many games do you get? Each has 3 games, 6, and you get 2 game systems. Or if you had a tricycle has 1 seat and 3 wheels. If you have 5 tricycles, how many wheels are there? 5 tricycles. 3 times 5, 15. How many seats on 5 tricycles? 5. Okay, so you understand the concept. It's just weird because it's these funny symbols that I'm making you look at. I'm sorry. Determine the number of each atom, each type of atom in the following formulas. So we're looking for a list here, basically. Each element has a capital letter. Some of them have a lowercase letter as well. But there's 1, 2, 3 capital letters. That tells us there's 3 different elements. There's potassium, there's sulfur, and there's oxygen. And they're asking us how many potassium atoms in the formula? 2. How many sulfur atoms? 1. How many oxygen atoms? 4. That's not so hard. Letter B. What elements do we have here? We have Al, we have capital S, and we have capital O. Aluminum, sulfur, and oxygen. How many aluminum atoms? 2. How many sulfur atoms? 3, right? Because there's this shrink wrap here. We have these packages, and we have 3 of them. How many oxygens? 12. Does that make sense? There are actually different types of chemical formulas. There's even more types than we're going to talk about in this class. Empirical is a word that means by experiment. So this is a practical formula. Empirical formulas give the relative number of atoms of each element in a compound. A molecular formula gives the actual numbers of atoms of each element in a mole. I'm sorry, a molecule. We haven't talked about moles yet. A molecule. So how many atoms in one molecule? That's the molecular formula. And then we also have structural formulas which help us to understand how those atoms are actually connected in the molecule. We often use molecular models, and we've seen pictures, because pictures are really, really helpful. I am a very visual person. I need to be able to see things, and if I can't actually physically see it, I need to be able to imagine a picture of it in my head. Not everyone is visual, but a lot of people are. And especially for this, where the actual atoms and molecules are far too small to see, it's helpful to have models of them that help us to understand what they're doing. So we sometimes use molecular models. And these are 3-dimensional representations. We can make ball and stick models where we actually have little balls and little sticks, and they're like chemists' tinker toys, and you can stick them together. It's really kind of fun. Then we also have space-filling models. And this more closely represents what the atom or molecule would look like if we could actually see it. If we could, blow it up to visible size, what might it look like? What are these guys doing here? We tend to color code the models so that we can tell the difference between the different atoms. You don't need to memorize those. It's just for example. And it's always nice to get some color on the slides. So here's a comparison of these different types of formulas for methane. This is the molecular formula for methane. Methane is CH4. It has 1 carbon and 4 hydrogen atoms. That does not tell us how those are connected, though. Are all the hydrogens connected in a line with the carbon at the end? Are they making a ring around the rosy kind of thing? What are they doing? So the structural formula helps us to understand how they're connected to each other. The carbon's actually in the middle, and it's attached to each of the 4 hydrogen atoms. And at this point, there is no way for you to know that. I'm just telling you that. We'll learn more about that. A ball and stick model is going to represent how those atoms are arranged in 3-dimensional space. They're actually not flat as a pancake like this. They actually make a 3-dimensional shape. This helps us to see the bonds and the geometry, but this is probably a much better representation of what that molecule actually looks like. So this is useful for some things, and this is more useful for other things. This is harder to see the geometry of the molecule, but we see that there are not big gaps between the hydrogen and the carbon atoms.